efficiency. And just check everyone.
Hey, online chat, can you guys hear me clearly? Oh, they can hear me. Great. And yeah, if this is going to be recorded, so.
Just making sure.
Oh,
I
oops.
recorded it. I'm gonna join on my phone. Yeah.
Yeah. Okay. It's recording. Easy.
I joined my phone. I was able to join this phone.
Okay. Okay.
Should I make it easier? You go full screen.
No, yeah. Nah.
And then just see the pen button.
Yeah. Right. I'll need to switch between sections. So yeah. Easy. Is there a more convenient place for me to sit that like doesn't? Okay. Cool. Let me just make sure everything's in order. So I've got the exam paper there. I can write. Okay, cool. Yeah, hey everyone. Thanks for coming to the crash course today. This is a lot bigger of a turnout than I expected. And you too, online chat. My name's Shai, and I'm going to be taking the crash course today. Before I get into things, I'd like to talk a little bit about just the style of Torsten's exams, because they're quite a bit different from what you might be conventionally used to. So the way it usually works is you have 2 hours. There's going to be 3 questions. There's usually a data sheet on these, and each question is split up into 5 parts. Each part is equally weighted, such that if you're looking to get in that HD range, then you should aim to answer all 5. So it's kind of a linear scaling in that sense. With a lot of these questions, there's no really set way to memorize how to answer these questions. Most of it is going to be applying your intuition or your knowledge that you learned in the lectures, because no question is going to be the same. He hardly ever recycles questions. So with this crash course, I'm going to aim to sort of give you an idea of how to critically approach his problems and sort of how to think about answering them, because a lot of the marks come from like stating assumptions and showing him that you understand the problem rather than actually arriving at a solution. There are multiple ways to answer these questions oftentimes, which is why you'll see on his website he says suggested solutions. Just because he has a solution to one of the design questions doesn't mean it's the only solution. Obviously, there's good and bad solutions, and that's really up to him as a marker to decide. Okay, so I'm going to be doing 2023, which is my paper. Cool. I think I'd like to do question 1 first, because it's a pretty interesting question. So I'll have a bit of a read. So a mixed analog digital electronic system uses a resistive sensor RS arranged in a bridge with 3 other sensors shown in figure 1A. In an attempt to read the sensor output VSO, this is fed into the input of an ADC, whose partial data sheet can be found at the beginning of this exam paper. The ADC serial interface is connected to a CMOS microcontroller, and the system uses a single power supply of 3.3 volts and a reference voltage generator U1, which provides the ADC and the sensor bridge with a reference voltage VREF, which is 2 volts. Some known circuit parameters are shown in figure 1B, and he gives you a couple of values. Most of these are in the question, but so he gives you RO, which is 1 mega ohm. And the first question says that there's a requirement that VSO has to be greater than 50 millivolts, which dictates a maximum value for RS. Find an expression for VSO and hence find RS max. So this first question is pretty straightforward. There's a requirement on VSO, which is this differential voltage between in plus and in minus. So I'm just going to draw this. I'm just going to draw this as a voltage divider, because it's going to make it a lot easier to see what's actually going on. So you've got your VREF, and then you've got your bridge right here, which is going to be RO, and there's RS there and RO. So pay attention to the polarity of VSO. So the positive is taken at in plus and negative is taken as in minus. So it's actually so plus here, minus here, and that's your VSO. So hopefully it's not too difficult for you to see that this is just a straightforward voltage divider. So VSO is equal to RO divided by RO plus RS times VRF minus a half VRF, because you've just got two equal resistances, which are RO. And this is required to be greater than 50 millivolts. Great. So I'm going to do some simplification. So you got RO plus RS times 2, because VRF is 2. And then this is a half times 1, sorry, times 2 is greater than 50 millivolts. I'm going to get out my calculator that I bought. Okay. So that gets you 2RO over RO plus RS is greater than 1.05. So RO is greater than or equal to what's 1.05 divided by 2? 0.525 RO plus RS. Cool. So that gets you RS is less than or equal to 904.7 kiloohms, assuming that RO is 1 mega ohm. Cool. So that dictates a maximum value on the sensor. It can't be any more than this. RS max equals 904.7 kiloohms. Cool. Any questions? Nope. I'm going to assume that's fine. Cool. Easy peasy. So the next part gives us some more info. Keep in mind that whenever you see these little paragraphs in between, that applies to the rest of the problem, unless stated otherwise. Yeah, this may or may not be useful, but yeah. So it's assumed that the microcontroller logic input levels VIH and VIL are the same as for the ADC. We denote the output logic levels for the ADC by VOH ADC and VOL ADC, and the noise margins for the signal D out by NMHD and NMLD. So the ADC has an output D out, and that interfaces with the microcontroller, looking at the diagram, and it just gives you that the logic, input levels are the same. And it asks you to estimate VOH ADC and VOL ADC, and hence find the noise margins. Cool. So I'll just do that here. Cool. So since in the question they don't really give you anything to go off of for these noise margins, this might be a sign that you need to consult the data sheet, which is provided at the beginning of the paper. So there we go. So if I scroll down to here, where it says digital input and output, it should have, so VOL as 4.1 volts, and VOH is 4.1 volts and VOL is 0.4 volts. So from the data sheet, VOH equals 4.1 volts and VOL equals 0.4 volts. One thing that you might notice is you've got the high voltage there as 4.1 volts, but we're using a supply voltage of 3.3 volts. And that's because in the testing conditions, there you go, VDD is 4.5 volts. So this is at VDD equals 4.5 volts. So what do we do in this case? Well, I think the most straightforward thing you can do is assume that to scale it down to 3.3 volts, you just assume that the voltage margins stay constant, just like an op amp, so that you have the same margin on either side. So you should probably state this as well, just so that in the case you get something wrong, Torsten at least knows what you were thinking, and if that's right, then all good. So assuming voltage margins stay constant as you scale down the supply voltage, then your VOH ADC is going to be, so what's the margin between 4.5 and 4.1? That's just 0.4. So you would expect the margin to stay the same, such that VOH is 2.9 volts, and VOL ADC is just going to be 0.4 volts because ground is 0 volts in both cases. Cool. Now we need to find the noise margins. So since this is an open book exam, you will probably have this equation in your notes, so you don't need to memorize it. But the high noise margin is defined as VOH of the ADC minus VIH. Has the screen dropped out for anyone else? Oh, can you guys see the screen? Have I stopped sharing? Oh, I'm not sharing. Okay, that's perfect. Okay, I can fix that in just a sec. Entire screen. Okay, sorry about that. Okay, you guys should be able to see. Okay, great. I haven't written much for part B. It's just I've written down the output high voltage from the data sheet, which you can find at the beginning of the exam paper, and that's at the VDD of 4.5. And then I've just used that margin to scale it down to 3.3 volts. And now I'm doing noise margins. So we need VIH. Why doesn't ADC have a digital input? It doesn't. It has a digital output because that's what an ADC will do. So this Wheatstone bridge is going to generate some analog voltage according to how RS changes, which is a sensor. That differential voltage between in plus and in minus is picked up by the ADC. That ADC converts it into a digital code, which is D out. D out can be multiple bits, but it's not really helpful to show that in the exam paper, which is why he just has one output. And that goes into a microcontroller, which can read that like binary number. And so you can do whatever signal processing you want on that end. So we're looking at the noise margins between what the ADC outputs and what the microcontroller takes in as a voltage level. But the same way that you interface between like two logic chips, it's the exact same. So maybe I should clarify. So this would be VIH, sorry, not ADC, microcontroller. And the noise margin low would be VIL microcontroller minus VOL ADC. Okay. Now we told you to assume that it's got the same VIH as the ADC. That was an assumption that the question gave you. So once again, we can go to the data sheet and look at VIL, which is always which is always 0.3 VDD, and VIH, which is always 0.7 VDD. So that's those two right there. And we know VDD, so we can just straight up calculate that. So the high noise margins would be 2.9 minus 0.7 times 3.3, and the low noise margins would be 0.4. Oh, sorry. it would be 0.3 times 3.3 minus 0.4. Okay, so I'm just going to put that into my calculator. So 2.9 minus 0.7 times 3.3 gives you 0.59 volts. And the low noise margin gives you also 0.59. Yep. Does that make sense? Are people still confused?
What's a good noise margin to usually have?
What's a good noise margin to usually have? I think it really depends on the chip and what you're trying to do. Obviously, you don't want it to be too large. Otherwise, you're kind of starting to move away from having like defined logic levels. And it might be harder to like interface with other chips maybe. You don't want it to be too low though, because to account for like the variation in the chips going like high or low. So honestly, I probably couldn't tell you what a good noise margin is to have. It probably just depends. But when you look at it, and like when you're looking at like this exam paper and come up with a figure of 0.6 volts, like, I mean, it seems fairly reasonable because it's like at least less than a volt. I don't know. You just kind of have to, I don't know, thug it out. Yeah. Okay, so part C is, what is part C? Okay, so we've got another little comment there. So the system uses a 2-layer PCB with a single combined analog to digital ground plane on one side. The system power supply VDD is generated by a single 3.3 volt linear regulator and needs to be distributed across the PCB, possibly aided by support components. Sketch how the power supply should be distributed on the PCB. So here he's trying to give you a bit of a hint. What do you think he could mean by support components on a PCB? Yeah, that would be my decoupling capacitors. Yeah, that would be my first assumption. If we're talking about power. So as to how to actually lay out the board, all of you hopefully have done lab 3. So you would have investigated the effects of noisy digital power supply coupling to the analog domain. And obviously that causes some undesirable behavior in your analog circuits, which can be pretty disruptive to your sensor. So I think to approach this question, you should probably, I think it's all right to write out like what you think. So for example, how should power be routed? You can make reference to lab 3 if you want. Why might we want to route power in this way? And obviously support components, yeah, you can talk about the coupling and why it's needed. So the coupling is needed to ensure a stable power supply. So when you're routing power, if I just draw the LDO here, in Torsten's lectures, he goes into a bit of detail on how you should do this, but essentially you want to separate, you want to route your digital power tracks and your analog power tracks separately so that there's less chance for them to couple. So what he draws in his solution is something like this, where you have your microcontroller here, and that's aided by a decoupling capacitor. And then you've got your analog. So this would go to the ADC. So there's your ADC. What else is there? All right, you also have the reference chip. So that would be down here. Right there. That's your reference chip. And so that provides the VREF for all your analog components. So all your analog components would be routed there. So that would be like your Wheatstone bridge with your sensor and any other analog parts that you have in a circuit that is not showing there. And then you'd probably have other digital stuff there. So other digital. So this would be like your VDD, and then this is like your analog VCC or whatever. What you might want to do with all of these is also just have a bigger decoupling capacitor on the output of the LDO. Usually LDO data sheets will tell you how to like route the decoupling capacitor and like what size it should be. But usually, since it needs to handle the supplies of all these other circuits, it would need to be bigger than the individual decoupling capacitors you place on things like the microcontroller, ADC, and the reference voltage generator. So yeah, cool. Hopefully I've explained that well enough. Does anyone have any questions about this part?
Would we ever worry about doing like polygons per hour, or just SketchUp?
Would you ever have to worry about like sketching polygons? Maybe there could be a questions where he asks you like sketch how the power plane would look like, or sketch how the analog and digital power planes would look like, but it's usually not very like complex. Like it will be a pretty simple circuit. But yeah, I think you could be asked to do something like that. Yeah, cool. Would you consider an ADC a digital component or analog? It's really both. I mean, it's a mixed signal sort of thing. I think you're asking in a sense that like, are you asking in the context of like where to route power? Like I would, like in his question, in his solution, he routes that power separately, because you don't want the noisy digital VDD coupling to the ADC supply voltage, because that can then couple to the sensitive analog parts and cause some weird stuff to happen. But yeah, I would consider an ADC just mixed signal, because it really is meant to interface between the analog and the digital domain. So it takes in analog inputs and it'll have a digital output. I'm leaning more on the analog side, but yeah. Okay. So part D, the attempt to design with the resistor bridge directly connected to the ADC inputs doesn't work. Explain which issues there are with part of the design. So I think when I did this question, I think I only identified one of the issues. That's the thing. Sometimes there's multiple issues that you just gotta have to look for. Obviously part D is a little bit tougher than the previous parts. You'll usually find this is typical of his questions in there. The latter questions get a bit more hectic. So what are the possible reasons that this circuit wouldn't work with the ADC? We have to think about, are there requirements that the ADC has, maybe on what like voltage it takes in? That would be one thing to consider. The other thing that you would need to consider is a little bit harder to see, but out of curiosity, does anyone who hasn't attempted this paper have any clues on what issues there are in this circuit? It's not immediately easy to see. Sorry? Common mode voltage. Actually, yes, I think that's one of the first issues. Yeah, I'll get into that. Yep. That's yeah, I'll get into that. The other issue is you have this sensor right here, which is very high impedance. How do I know this? Because RO is a mega ohm, right? And RS is like at most like 900 kiloohms, basically a mega ohm. So you have a very large noise. I mean, I don't think so, because I guess you could talk about noise, but I'm not sure how you would, just going off of large resistance. Yeah, so typically larger resistors will have more thermal noise, but that's more of an issue in the sensor itself rather than how it interfaces with the ADC. This question is like asking, is there anything that makes this not work? Like noise obviously is a factor when you're considering, making a sensor, but it wouldn't make something necessarily not work. Noise obviously might affect your signal to noise ratio, and so that might prohibit you from getting a certain effective number of bits, but that won't necessarily make things not work. So when you have a large impedance in your sensor, you have a voltage divider, right? So one leg of the voltage divider or one leg of the bridge is just fixed at half VDD, half VREF, and the other is varying because your sensor resistance will vary, RS, and then you've got RO there. Right. So when you have a large input impedance like this, to make the assumption that this is a voltage divider, you need to assume that there is basically no current going into the ADC. Why? Because if there is current going into the ADC, then it's no longer a straightforward voltage divider. So that leakage current is going to cause this nodal voltage to drop a little bit, and it's going to create an offset in your ADC. So yeah, so you want the input. So how large would you want the ADC input impedance to be? Yeah, larger than the impedance that it sees looking into the voltage divider. That's right. So the data sheet won't give you the input resistance, but it will give you a leakage current, which is going to tell you the same thing. So what is the RTH that the ADC inputs actually see? So if we're talking about in minus, the RTH that it sees is going to be, well, if you just do a Thevenin calculation, it's just a parallel combination of those two resistances. So RO in parallel with RO, which is 500 kiloohms. Looking into the in plus, it'll see the same thing if RS is RS max. I'm going to take the worst case, which is 500 kiloohms, because that's the largest the input impedance can be. So how large is the offset voltage that it generates? Why does it generate an offset voltage? Because that leakage current that is now going to go through this Thevenin resistance that it sees, where it's 2 ROs in parallel, that's going to go into the sensor. So I leakage. So that static current that goes into the ADC obviously creates a voltage that is felt as an offset. So we can calculate how large this offset voltage is. So VOS is I leakage times RTH, and we can consult the data sheet. It's where would it be? There we go, analog inputs. So sorry, let me just rub this out. So leakage current, it says, is at most 1 microamps. So if we want to calculate the worst case voltage offset, we would use that. So worst case VOS is 1 microamps times 500 K, which gives you 0.5 volts. Is this okay? No? Why not? It's big. Well, How do we know it's big? Well, I mean, if you have your reference voltage is 2 volts, and that takes up nearly a quarter of your full range, then yeah, that might be an issue. Because then you essentially have no dynamic range if that offset becomes too big. So obviously it would be good to mention that. I'm not going to write it down, but you just say that it's large compared to the VREF, or you make a judgment, say it's unacceptable. So the other issue is the fact that what I mentioned earlier, which is that requirements on in plus and in minus. So if you look at analog inputs, yeah, the input voltage range of in minus is VSS minus 100 millivolts to VSS plus 100 millivolts. So V in minus has to be fixed between whatever VSS is plus or minus 0.1 volts. VSS is 0 in this case. On the diagram, there you go, it's 0. So V in minus is confined to within 100 millivolts of ground, basically. That is a requirement. But if you look on the schematic, V in minus is actually just tied to 1 volt because it's tied to that half ERF node right here. So obviously this violates this condition. So this condition, this condition is violated. Cool. Yeah, I think those were the two issues. Because on the data sheet, it gives you a range for the analog inputs. Input voltage range of in minus should be VSS minus 100 millivolts to VSS plus 100. So there's a min and a max. So those are requirements for your parameter of the in minus voltage. And so you're violating that in this diagram, so the ADC probably won't work. Okay. Does anyone have any questions about that? Because, so why, how is it being violated? Because if you look here on the schematic, the in minus voltage, if we trace it, it attaches to this node, and that's at 1 volt. So yeah, that obviously is violated. Okay. Part E. Right. So part E is, part E is a nice question. To improve the design, an amplifier with a voltage gain of 10 is to be inserted between the resistor bridge and the ADC. The amplifier may use operational amplifiers as gain elements. Design the amplifier and show how it is included in the design. So he's trying to give you a bit of a hint there when he says you may use operational amplifiers as gain elements. And obviously there are more than one solution, but there is one immediate one that I can see that would work for this. But I'll just go over how you would kind of think about this design question. So we need to fix the issue. So there's two issues. One issue is that V in minus needs to be basically at ground. The other issue is that the leakage current is too significant. So how would we solve leakage current being too significant? I think someone else already pointed it out before. Assuming you can't change the sensor. Okay, yeah, you can use a buffer. So if you have a buffered input, what you want to make sure is that that buffer has sufficiently little enough input leakage current such that it is basically negligible, and the offset that gets created is like, let's say, less than a least significant bit. So such that it doesn't like affect your measurements. Use instrumentation app with current in plus and in minus and inputs. Yep. So the reason an instrumentation amp works here is it has another thing, another desirable trait, which is that it will take the difference between two of its input. So it's a differential to single mode amplifier, which means that it will take the difference in plus and in minus, which is what we're really interested in because that's what the sensor is measuring. And you'll amplify that, and its output is single-ended, so it's just one voltage. So that allows us to fix the other issue where in minus needs to be grounded. So we can ground it, but use an instrumentation amplifier instead to amplify the voltage difference anyway between in plus and in minus, and feed that directly into the positive input of the ADC. So I'll draw what that looks like in case y'all are confused, because that is a lot of words. So you have VREF. Here is your resistance, your resistor bridge. Cool. So, and I'm basically just copying this from the lecture slide since it's been a while since I've had to look at instrumentation apps. But essentially, you have this sort of gag. Also, when he says design, it usually means pick values. So make sure you do that too. So let's say R1, and then this takes in an input. There's a feedback resistor, and this needs to be 9R1 because the inputs are non-inverting. So to have a gain of 10, you need 9 times R1. And yeah, so if you have it in this configuration, that gives you a 10 VSO at these terminals, where this is VSO. Okay. Yep. So then that goes into, so it has a buffered input, and that goes into an instrumentation amplifier that looks like, sorry, not instrumentation amplifier, difference amplifier that looks like this. Yeah. So, and this difference amplifier just has a gain of 1. Oh, and I missed a resistor. Well, there you go. So R1, 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 and it takes the difference such that you get 10 VSO here. If you do the difference amplifier the other way with the minus terminal over here, then it would produce a negative voltage since it would be like inverting, and that won't work because the ADC takes in only positive voltages. If you look at their requirements on VN plus in the data sheet. Right, so if we put that node into the ADC like this, such that in plus is the node that varies according to VSO, and we fix in minus at ground, this essentially solves both our issues, because now in minus, the requirement is not violated, and then in plus takes in the actual analog value such that the ADC can convert it into the D out. Right. Now you'd want to design values, but like there's not really, you can't really go wrong with any value of R that you pick as long as it's like kind of sensible. So you could say R1 equals 10 kiloohms or like 1 kiloohm, 100. I think it really doesn't matter. And that's a good thing that it doesn't matter, because if you just like put this circuit straight into a difference amplifier, then you have to worry about the impedance that it sees looking into this resistive divider. So an instrumentation amplifier solves that by just having the inputs buffered like this. Oh, this goes to ground. Yeah. So I guess a couple things you might want to say about this instrumentation amp. So one, yeah, you want to make sure the op amps have very low leakage current, like possibly in the pico amps or something, such that your voltage dividers actually look like voltage dividers, and the offset contributed by that leakage current is very insignificant. You'd also need the amplifiers to be rail to rail, because because this output here can be as large as Vref, I think. If you make the assumption that like RS can change between 0 and whatever its maximum value was, then essentially you could have this node going all the way to Vref, and so, or I guess, sorry, this node going all the way to Vref, and so you need the operational amplifier output voltage to be able to handle that, I guess. Yeah, does anyone have any questions about that? That was question 1. Yep. Are all the op amps single supply? Yeah, there would be. I don't see a reason why it, no, I think there would need, no, yeah, there would be single supply, because VSO, it says there's a requirement that, yeah, VSO is greater than 50 millivolts. So it can only be a positive, thing, a positive value. So that would mean that RS, yeah, that would mean that this voltage cannot go below 1 volt, because, or 1.05 volts, because that would make VSO negative, because you're taking the difference between that and the left node. So that would cause it to go negative, and yeah, it says VSO has to be greater than 50 millivolts. So actually, yeah, RS would be confined to like, yeah, there'll be like a minimum and a maximum, I think. You calculated the maximum, but yeah. So yeah, there'd be single supply. Okay. Yeah. So how are we going for time? We've consumed like 45 minutes. I think there'd be time to do maybe all of the questions, maybe a bit less than 3. Yeah, so no questions before I move on to question 2? Okay, easy. So question 2 gives you an anti-aliasing filter, which is just a Sallen key topology. Some of you that attempted the project might have looked at this for some reason. I remember seeing a couple of Sallen keys when I was marking reports. So it's based on an operational amplifier, which is U1, configured as an amplifier with low frequency gain of 10. Some known circuit parameters are shown. So it's dual supply, so +3, -3. There is the parameter V out can be, the magnitude can only be less than 2 volts. And R3 is 10 kiloohms. Assuming the op amp is ideal, the filter has a transfer function, H of S is that, given below, and component values must be chosen to ensure the circuit does not oscillate. So very rarely in a paper will Torsten make you do rigorous math like this. And when it does, he'll just make you rely on your basic quad 1 circuit analysis. But yeah, he would never give you something this difficult to derive, which is always a nice thing. So part A is what restrictions on component values must be imposed. So reading the question, it says it needs to be chosen such that the circuit doesn't oscillate. So does anyone have any ideas? Poles? Yep. So yeah, the response of the filter, the transfer function, is going to be a two-pole system since you have two capacitors there. So it's a second order filter, and you want to make sure that it's stable. Otherwise, you make an oscillator, which is not a filter. So question 2, part A. So the condition for stability, hopefully, or maybe, no, actually, most of you would not have taken control systems, but the condition for stability is that all the poles have to lie on the left side of the J omega or the complex plane. So they have to lie in this region, which means that the real part of whatever complex poles you may have has to lie on the left side. Cool. So yeah, writing out the transfer functions. Okay, so if you want to solve for the poles, you need to solve a quadratic, because so you have C1, C2, R1, R2, S squared plus C2, R2 minus 9, C2 minus 9C1, R1, yeah, R1 S plus 1. And you want to make that equal to 0 because that's how you solve for where the poles are. Let me know if I copied that wrong, but I think that's right. Okie dokie. So, oh, there's a plus. Oh, yeah, that's right. Yeah, there you go. I would have failed this question. So, well, I actually think I answered it, at least the first part. But anyways, so you want to make sure that the real part of the solution lies on the left side of the J omega, the complex plane. So S equals, surely you guys remember the quadratic formula? So this is going to look like minus C2 R2. Oh, you know what? It's easier if I go. So the real part of this has to be less than 0. And the real part of this is minus B on 2A. So what I'm assuming that this block is complex. But even in the case that it's not complex, that doesn't matter, because like if this is a real value, then it still gets trumped by that minus B term, since B is always greater than root B squared minus 4AC. You can convince yourself by doing the math. And that means that, yeah, no matter what real value this takes, it's always going to be, I guess, this B factor is always going to be bigger than that. So as long as this is less than 0, then you're all good. So minus B over 2A is less than 0, which means that minus B is less than 0, which means that minus C2 R2 plus 9, oh no, plus C2 minus 9 C1 R1 is less than 0. So that gives you that C2 R2 plus C2 minus 9 C1 R1 has to be greater than 0. And it didn't specify any particular component, so you're free to just leave it in that form, since yeah, it doesn't tell you anything more specific. Right, is that all good with everyone? All right, so part B. What's part B? Show in the circuit diagram all the random noise sources present in the circuit. This is a gift of a question because drawing noise sources is really easy. And I guess the only tough bit is remembering what are the noise sources in a circuit. So with resistors, you will typically have thermal noise associated with them. So R, Vn. Yep, and with capacitors, they are inherently noiseless devices. So assuming all the components are ideal, there will be no noise sources associated with capacitors. And the op amps have noise that can be modeled as a noise source here and a current noise source there. So that's your IN and your EN. Yeah, cool. So using those three, you can sketch the circuit. So you have your input voltage V in. There's your R1 and your voltage, your noise voltage VN1. And then I think there's a feedback. Yeah, there's a positive feedback path taken there. So C1. I always like drawing the noise sources separate. Like I would draw it on the right side instead of the left, because it makes in my experience, it makes the analysis a bit easier. But in this case, you're not doing any analysis, so it actually doesn't really matter. So VN2, and then I think you need your, I think there's a capacitor there, which is C2, and you have your EN of the op amp, and then your IN. And then you have your feedback, your gain of the op amp, which is just this. So VN3, R3, and then this would be 9R3, and I'll just call this VN9R3, and then that feeds to the output, or the output feeds into that, and this goes to the output too, and that's your V out. Cool. Yeah, I've drawn it. Hopefully no one has an issue with this, aside from the fact that the drawing looks terrible. Part C. The op amp has a low frequency power supply rejection ratio of 60 decibels. A low frequency signal with an amplitude of 1 millivolt appears at the filter output and is known to be caused by supply voltage variation. Find the amplitude of the supply voltage variation causing VOSS. So in this question, you're giving parameters, and you can kind of see where to go because it gives you the PSRR, and it also gives you the amplitude at the output caused by the supply ripple. So you're free to just use the power supply rejection ratio equation to math it out. So PSRR equals, so it's defined as the voltage gain over frequency divided by ACCS, where ACC I'm going to write as it's the change in V out over the change in VCC. So it's going to be VOSS over whatever delta VCC is. So that's what we want to find. So we have that it's 60 decibels, so 10 to the 60 on 20 equals the voltage gain. And now it said low frequency ripple. So from that, you can extrapolate that it's near DC. So the gain of the amplifier just reduces to 10, because if you look at the transfer function, well, actually, I think it says, yeah, it says that low frequency gain is 10. But you can also math it out from this transfer function, because when S is close to 0, this becomes 0, this becomes 0, and you've got 10. So yeah, so this would be 10 divided by ACC, which is VOSS divided by delta VCC by definition. So that means that delta VCC times 10 divided by VOSS is equal to 10 to the 60 on 20, which means that delta VCC is 10 to the 60 on 20 divided by 10, times VOSS, which is a millivolt. And if I put that into my calculator, that gives me 0.1 volts. So that is and that's an amplitude, because it said that the amplitude of VOSS was 1 millivolt. Okay, does this make sense? Anyone have any questions about that? Nope, all good. So part D is, in the following, it is assumed that R1 equals R2 equals R3 equals 10 kilo ohms. C1 is 500 pico and C2 is 5 nanofarads. A suitable op-amp must be chosen for the filter. In particular, the following op-amp parameters must be considered. So gain bandwidth product, input bias current, input offset voltage, and common mode input voltage range. So this is a bit of a loaded question. The question is discuss suitable requirements for these 4 op-amp parameters. This is a bit of a loaded question because there's a lot to talk about. So I'll go over what you need to say. And I'll just speak because there's too much for me to write. But there will be answers to this that I've made and I'll share afterwards. So with gain bandwidth product, actually most of you should be able to answer this because I saw a lot of you struggling in the project to get the right cutoff frequency, and a lot of you measured it to be smaller than what you expect, and that was because the op-amp was bottlenecking your filter. So what requirement needs to be on the gain bandwidth product of the op-amp you use? Does anyone have any clue? Right, yeah, so what you're saying is the gain bandwidth product of the op-amp itself needs to be significantly larger than the gain bandwidth product of your filter. And that's correct. Why that is because for a given gain, if the bandwidth of your op-amp is not large enough, then in addition to the filter attenuation, you're also going to get some of that op-amp attenuation from its first order pole response. And you don't want that because then your filter won't have the right 3 dB cutoff that you designed for, and that may be an issue depending on the circuit and the application. So the gain bandwidth product should be high enough such that the op-amp doesn't bottleneck your filter. If the bandwidth is large enough for a given gain, then it will have some extra attenuation on top of the filter. Now, because this question gives you values on the resistors and capacitors, that's usually a hint that Torsten wants you to do some sort of calculation. So recall that a second order transfer function can be written like, for a low pass filter, can be written like this. So AV omega squared, S squared plus omega naught on QS plus 1. Sorry, plus omega squared, omega naught squared. And if you compare coefficients to this transfer function, so you need to divide by this term to get the coefficient of S squared to be 1. But you'd get that the last term is 1 on R1, R2, C1, C2, which is congruent to omega naught squared. It's the same as omega naught squared, which means that the cutoff frequency of your circuit is going to be 1 on R1, R2, C1, C2. Or you can just memorize that that's the cutoff frequency, but you can always math it out. So if I sub in 10 kiloohms and so 500 picofarads and 5 nanofarads, and divide by 2 pi to get frequency, you get that the frequency is 10.07 kilohertz. Okay, so the gain bandwidth product of your filter is just the low frequency gain times f0, which is 100, basically 100 kilohertz, since your low frequency gain is 10. So the gain bandwidth of your op amp should be larger than that. How large? It's really up to you to say. I would probably put it like 10 times larger. So gain bandwidth op amp, much larger than that. So let's say about like a megahertz, or you could say 10 megahertz. I think 1 megahertz would probably cut it. Yeah. The other two, like offset, there was like offset voltage and input offset voltage and input bias currents. They're kind of semi-related. So I think in this one it's a bit tricky to figure out what he's getting at, but obviously intuitively we understand that the offset voltage needs to be small, right? That's just, I guess, basic op amp rules, or not rules, but you want the offset voltage to be fairly small. How small is more of the issue, because he does do a calculation in his solutions that pretty much makes the he puts a design constraint on VOS at the output such that it is as significant at most as the error already introduced by the supply voltage ripple, which is a millivolt at the output. So he says that VOS has to be a lot smaller than, or like smaller than or equal to 1 millivolt, because 1 millivolt is like the, I think he calls it the tolerable error. But yeah, I think you can really argue, I think it would honestly be fine if you argue your own sort of requirement on output voltage. I think it's a bit easier to justify if you like use concrete numbers, but that actually come from somewhere. So the 1 millivolt, which comes from the supply ripple rejection. So that's input offset voltage. Input bias current, likewise, you don't want to be super large, because in combination with whatever resistances you have, that creates an offset voltage in itself. So what does the actual, I think he actually calculates that offset. So to give you a brief recap on 2123 theory, because Lord knows I didn't really retain anything from that course until I went back to demo it. But so input bias currents, you have your IB minus like this and your IB plus this. And so the offset voltage contributed, and so these are like static DC currents. So what the op amp looks like in terms of the equivalent resistances that they see is you have R1 and R2 here. Capacitors are all open circuits. This goes into your negative terminal. So that's these two. And then on the positive terminal, you have the like parallel combination of those resistances. Because again, if you do a Thevenin calculation, I think you zero the output of the op amp because it's not turned on. So this is basically just grounded. So 9R1, sorry, 9R3 in parallel with R3. There you go. So what he does is he calculates the offset voltage the input offset voltage, which so you would need to, for the, I think this is output referred. So you need to scale that to the input by dividing by the gain. So this would be 0.1 millivolts. Because it said input offset voltage. I was talking about the output, so you need to scale that to input. Same here, he calculates the input offset voltage as a result of the bias currents. So he did R1 plus R2, IB minus, subtract 9R3 in parallel with R3 IB plus. It doesn't matter which of these IBs you put first, because you just take the magnitude. One question you might ask is, why are we not adding the offset voltages contributed by these bias currents? Why are we subtracting? Well, if you kind of think about it, if both of these currents contribute a voltage, offset voltage that is like the same polarity, then that actually just cancels out. So you actually don't get any offset voltage. So you'd want to take the difference because the input differential pair is symmetrical. So you'd want to take the difference to actually calculate what offset you would have instead of the summation. Because yeah, like I said, if they both contribute the same, then that gives you 0. There's no offset, so it doesn't actually make sense to add them. So if you math that out, I'm not going to put it into my calculator, but you and you assume that the input bias currents are like the same to make it easier. And I think you solve it to be, yeah, I think he makes it so that the input voltage has to be no less than a millivolt as per the previous part. Sorry, a tenth of a millivolt, so 0.1 millivolts. You get IB is like 9 nanoamps. So IB has to be less than 9 nanoamps. Yeah. The last parameter is common mode input voltage range. So what is common mode input voltage range? Well, it's just defined in terms of the voltage that's common to both inputs of the op-amp. So so the common mode input voltage is V positive plus V negative divided by 2, where V positive is the voltage at the positive terminal, the non-inverting terminal, and V negative is the voltage at the inverting terminal. And an op-amp under negative feedback has VP equals Vn, so it's just equal to like Vp plus Vp over 2, which is Vp. Why am I using Vp instead of Vn? Because the input voltage is at the non-inverting, or it goes into the non-inverting terminal, and because V out is at most 2 volts, then ignoring the attenuation of the filter, the largest value that Vin can attain is a tenth of that, since the gain is 10. So Vin equals Vp under low frequency, because these capacitors are open circuit. So you just have Vp equals Vin. So yeah, between 0.2 and minus 0.2, because V out at most was less than 2 volts. So dividing by 10, that gets you 0.2. And that's actually your, that actually puts a minimum requirement on your input voltage range, your common mode input voltage range, because if you have any lower than this, so let's say it was like between 0.1, then there could be a case where Vin is 0.2 volts, like your signal, and that will go into the positive terminal and violate this condition. So what that might typically do in an op-amp is it will cause distortion, which obviously is not good. Yeah, THG guys. So this is a minimum requirement. On common mode input voltage range. Yeah. All right. So that was a pretty loaded question. Does anyone have any queries or things they didn't understand? Because I feel like this is a pretty tough question to answer in full. Yeah, to which part? Yep. Vn, like so yeah, V negative. So the voltage at the like non-inverting, sorry, the inverting, because an op amp under negative feedback, golden rules, Vp equals Vn. Yeah. Yeah. All good. Sweet. I hope the online people are good too, and that I haven't like disconnected. No, okay, I'm still sharing. Cool. Yeah. Okay. Cool. Okay, part E is a bit of a banger because I remember looking at this and just going, what the heck? And also the solution to this, I had a look, is a little confusing. So hopefully I'm going to clear some of that up. So an accelerated lifetime test is carried out on the filter with a test temperature of 120 degrees Celsius. After a week of testing, 3 devices out of 10 have failed. It is assumed that the use temperature is 60 degrees and that the dominating failure mode activation energy is that 0.9 electron volts, and that the failure rate has an Arrhenius temperature dependency of that, but is otherwise constant. So it's dependent on temperature, but constant with time. Then it gives you Boltzmann's constant. Find an estimate for the mean time to failure of devices in the field. So yeah, this is a pretty tough question, I think. And so I'm going to try my best to explain how Torsten derives the answer in his solutions. So I'm going to define some parameters. So FTT is the, like big F of T underscore T is the fraction of failed devices at a temperature t-test. Lambda of T underscore T is the hazard function, or the failure rate at a specific temperature, which you can assume is constant with time, but varies with temperature. Little f of T is just defined as the differential of big F. And AF, which is the acceleration factor that accounts for the hot temperature test. So we've got TT, which is the testing temperature, and TU, which is the use temperature. So test, use. Okay. Yes, interesting. Actually, I don't think I need this parameter. Yeah, I don't need that. Okay. So from the lecture slides, f of T underscore T is 1 minus e to the minus lambda times time. This is for an exponential distribution, which applies in this case. So where f again is a fraction of failed devices. So if you make that equal to NF on NS, I think 3 on 10, you can actually solve for lambda because that's the only variable in your equation. So what this means is after a week of testing, 7 days, after a week of testing, this many devices have failed. And this is in terms of the hazard function. So it actually allows you to solve for it. When you do that, you get this expression that I have in my notes, minus ln 1 minus nf on ns divided by t hot. And Torsten does it in hours. You can use whatever you like. That gives you 2.12 times 10 to the minus 3 failures per hour. He also does another calculation for this hazard function. where he assumes that it's the distribution is linear, I think. So what he assumes is that lambda is, so alternatively, this is f, so the total number of failures per time. So that's 3 on 10 divided by like 7 days, however much that is in hours. So you can do that as well, as long as you state your assumption. That's also fine. They give you slightly different answers, but overall, they shouldn't be too different, and you'll still be able to get the marks whichever way you do. Me personally, I'm more of a like rigorous math person, so I opted to do this question, to solve this question using the first method, where you actually calculate the hazard function. But either way is fine. Okay, next we need the acceleration factor because we're doing an accelerated lifetime test. So this is defined as this. So lambda t test divided by lambda t use, which for the Arrhenius distribution or whatever it's called, Arrhenius temperature dependency, it is defined as e to the EA over K T use, where T use is in Kelvin. Just be careful because Boltzmann constant is in terms of Kelvin. Yep. And I'm not going to math this out, but if you do that, you get an acceleration factor of approximately 120. And now the only thing that's left for us to find is the mean time till failure. So by definition, the mean time till failure is defined as on the cumulative distribution function for the failures, capital F of t. It is the time at which half of the total devices have failed. That doesn't really look like a half. There you go. So a half of the total devices have failed. So making that equality using f of t. Sorry, that should be capital. 1 minus e to the minus lambda t. Mean time till failure. This would be, yeah, a half, because a half of the total devices have failed. So solving that for mean time till failure gets you. Maybe I'll just do it now because it might be easy to see if I do it myself. So if I move this one to the other side, you get minus a half equals minus e to the minus lambda t. So minus lambda t is, so cancel the minus, you just get ln a half, and times everything by -1, you get ln2 because of log rules, which means that t mean time till failure is ln2 times 1 over lambda t, well, whatever temperature you use. And so how this relates to the acceleration factor is the mean time till failure in the use temperature is just the acceleration factor times the mean time till temperature at the testing temperature. So that is just 120 multiplied by the mean time till failure. We've got lambda of t test, which means that we can just use that equation. So this is 120 times ln2 times 1 divided by 2.12 times 10 to the minus 3. And that gets you, I'll actually do that now. ln2 times 1 over 2.12 times 10 to the minus 3. So that gets you 3.92 times 10 to the 4 hours, which you can convert to years. So there's 24 hours in a day and 365 of those in a year. So if I divide by 24 and then divide by 365, you get 4.48 years, something like that. Yeah. So yeah, that was a bit of a question. If you use the other method where you assume the like simpler equation that for lambda, you get something pretty much similar. I think you get like 3.91 times 10 to the, no, sorry, you get something, I don't remember what you get, but you get something that's not that much different. Either way is fine. Does anyone have any questions?
What was the assumption for that simpler version of lambda?
What was the assumption? The assumption is that, did I write it down? Oh yeah. Yeah, so the assumption that it's not like an exponential dependency, it's just like linear, which is that so lambda is a like failure rate per time. So he's just saying lambda is approximately equal to the number of failures divided by the total time that has passed to get those failures. So yeah, you can do that. That's also fine. But yeah, I think I remember being confused where the ln2 came from till I actually tried solving the question. Yep. Okay. Does anyone have any queries before I move to question 3? Oop. Okie dokie. Yeah, question 3 is interesting. I like all the questions in this paper. Actually, quite fond of this paper. So figure 3a shows a class D type power amplifier implemented with 2 MOS transistors. So that's M1 and M2. And 2 digital CMOS inverting buffers, U3A and U3B. Oops. And the power amplifier drives a load resistance RL, controlled by, which is and it's controlled by microcontroller U2, and is powered from single supply linear regulator U1. The inverting buffers share a package and have a supply decoupling capacitor CC3. The transistor gate capacitances are explicitly drawn in the schematic. Some known circuit some known circuit parameters are shown in figure 3b. Okay. Yeah, so in the I don't think he's gone over class D amplifiers too in depth. One application where you might see them in is audio amplifiers. So you can, the different class of power amplifiers you can find for being used for speakers. So typically that RL will be the speaker's impedance, which is usually very small. So in the question, it's 4 ohms. You can have speakers with 8 ohms. Also keep in mind that the speaker has not just resistance, but inductance and capacitance that is not shown in this question. The way the circuit actually works is the microcontroller outputs a series of like 1s and 0s, and that gets fed into the buffers, the inverting buffers, and that 1s and 0s turn either M1 on and M2 off, or vice versa, so that you get like a square wave at the output. And if you low pass filter that square wave, or if you take a moving average, that gets you sine waves, and so that gets you your audio out, I guess. Yeah, so what that means is, and he hasn't drawn the low pass filter. Sometimes you can even use the speaker itself as the low pass filter, or you can just implement it with a, however you might implement the low pass filter, but it's not shown in the circuit because it's not really relevant, and just makes the analysis a bit, or it just makes it harder to figure out what's going on. But yeah, that's how this circuit works. Yes. All right. On to part A. So the U3A output can be modeled as a resistance, which in conjunction with CG1 forms a first order network that determines the node A transition times. An excerpt from the data sheet is shown to the right. So it gives you the VOH and IOH and the VOL and IOL. Estimate the worst case R3A and hence node A rise time TRA. Cool. So the clue here is the output resistance forms a first order network that determines the rise time. First order network means what exactly? Anyone? Exactly, yeah, RC. So Torsten's just telling you there that you can model this as a simple RC. Half the problem with these questions is deciding how you need to model a certain problem. And in this case, it's just a term. The rise time is purely determined by an RC time constant and nothing else. Hopefully you should, or if you're not sure why, just think of back to ELEC3111 when you were doing all those circuits with their switches, and the time constant just depends on RC, and that in turn determines the rise time, and it doesn't actually depend on like whatever voltages you have in the circuit. It's literally just dependent on the RC time constant. So question 3. Oh, whoops. So question, oh, hello. Question 3, part A. And he says that the output can be modeled as a resistance. Why this is, I guess I could go into a bit of explanation as to why, because it's not really obvious. So with a buffer, one way that you can implement this in CMOS technology is just, so you have a PMOS gate there, and that goes to the supply voltage. And then you've got an NMOS gate there, and that goes to ground, and your output is taken here. So if in goes high, then the PMOS transistor turns on and the NMOS turns off, so the output swings high. Sorry, if in goes high, the NMOS turns on, so the output sinks to ground. And if in is low, then the PMOS turns on and the output gets pulled up to high. So it's an inverter. And what you can do is model the on resistance of these transistors as just a resistance. Oh, obviously that's an approximation, and he's telling you that it is valid to make that approximation. So what that will look like is R3A, R3A, okay, yeah, it tells you, it wants you to estimate worst case R3A. And then you have your load resistance here, RL, since the other transistor is turned off, or you can have R3B and the load resistance. So so maybe it's more helpful if I draw it like this way. So I think the way that you model it is just say VCC, and then you have your VOH here, and that's for the high case, and then for the low case you have VOL and that resistance there. And each of these cases has an associated current that flows, which is IOH and IOL respectively. And that allows you to calculate a value or estimate a value for the on resistance. In real life, it's a bit more complex than that, but he's telling you that you can make this assumption. So that's what we're going to do. So R3A, so I mean, using just Ohm's law, right? V equals IR, which means that R equals V on I. So R3A can be VCC minus VOH divided by IOH, which in both cases it's given as 32 milliamps. The only reason why this might be the only reason why there's a negative sign on one of them is because like the convention is you take the output current as going into the input. So if one of these cases it's actually sourcing, not sinking, so that's why. But you just use the magnitude; it doesn't matter. So so VCC is 3.3, so 3.3 minus 3.3 minus so VOH is 2 and VOL is 0.5. So 2 over 32 milliamps. That gets you I get to 40.625 ohms. I think there's actually a mistake in this paper where he does 3 instead of 3.3 or something. The other case is for the low case, which you just have VOL over IOH, which is just 0.5 divided by 32 milliamps, which is, that gives you 15.625 ohms. Since it asks you to find the worst case, this is in the context of rise time because it's proportional to R. So the worst case rise time corresponds to the biggest resistance, which is the 40.65 ohms. So this is the worst case resistance that you have. Worst case R3A. So you actually have to think about what is the worst case here. And because the question asks you to find the rise time, that means that you have to use that to figure out what your worst case is. Okay, so for the rise time, I'm going to throw this equation at you with no context, which is TR is ln9 RC. If you want to convince yourself why this is, I have provided a derivation for it in the solution to this crash course. It's also, also Torsten, I'm pretty sure, goes through it in his lectures, but that might be a bit harder to find. But yeah, you can just accept this equation for now, where R is the R3A, the worst case resistance, and C would be, well, what would C be in this case? What would be the dominating capacitance in this, in node A? Yeah, CG1. So, so T rise is just ln9 times 40.625 multiplied by the CG1, which is 100 picofarads. So 100 times 10 to the minus 12. And subbing that in gets you 8.9 nanoseconds. So 8.9 nanoseconds. Great. Yep, that's the rise time. Does anyone have any questions about part A? Online people are fine, I'm assuming. Okay. So part B, sketch the paths of the displacement currents in CG1 and CG2 when node X goes high, i.e. nodes A and B goes low. To avoid, to avoid drawing this whole circuit, I'm just gonna share my answers. So these are the answers that I wrote for this crash course. There you go. So because you have a decoupling capacitor there, CC3, when the node A and node B, so when, what transition is it? It's node X goes high. Okay, so node A and B goes low. So since node A went low, that means that CG1 gets charged because the other terminal of the capacitor is at VCC, which means that current flows downwards. So that's the green path that I've sketched in this question, in this diagram. So that goes from the supply decoupling capacitor into the capacitor, through the gate and to ground. So that's the path that takes. I pretty much just copied this from his lecture slides as well. So for the other capacitor, why did this suddenly glitch out? The other capacitor, CG2, needs to get discharged instead of charged, because node B goes low instead of high. Yeah, one node is, oh my God, please let me scroll. No, it's all good. My OneNote does this as well. Okay, so that's the red current that I sketched there. So because node B goes low, the current has to flow upwards. Since the capacitor is discharging, not charging, so the voltage is decreasing, not increasing. And it flows, yeah, from the capacitor to the chip and to ground. There's not much else to that question. I mainly just copied the lecture slides from like week 2, I think, for this. Yeah, I think one of the other thing you have to realize is that that current that charges CG1 comes from the decoupling capacitor. Since when you use decoupling capacitors, they become like the source of like where the current flows. They provide an alternate path for the current to flow, and that like stabilizes the voltage. Yeah, I basically just got it from like the week 2 lectures. Okay. So part C, which is find the maximum instantaneous power that you can deliver to RL. Ooh. Part C. Okay. So keep in mind it says instantaneous power. So you can literally just use V squared on R. There's no half there because that's average power. So, okay, yeah, so so your output stage would look like, yeah, you can model the transistors as on resistances. Again, does it actually give it to you what they are? Yes, it does. It gives you these parameters. So it gives you the on resistances of M1 and M2. So R on M1, you have your VCC, and then you have your load. Oh, yeah, my bad. I think I accidentally sketched this for the previous question. That doesn't, yeah, that was wrong. Whoops. But yeah, so what limits V out from going to VCC? It's this on resistance. Otherwise, if the transistor had no on resistance and it operated fully like a switch, then you could just pull it up to VCC. Yeah, so PL max is V out max whole squared divided by RL. That's instantaneous power. Now we just need to find V out max, I guess, which is just a voltage divider. So V out max is VCC multiplied by RL divided by RL plus R on M1. I'm using M1 because we want to look at maximum AC power. So that's when it gets pulled up high. So VCC is 3.3 volts. RL is 4 and R on is 0.3. So that gets you like 3.07 volts. And so squaring that and dividing by RL, which is 4 again, gets you 2.36 watts. Easy. Yeah, that's a max instantaneous power. Almost done. So part D tells you, in the following, it's assumed that the maximum supply current is 800 milliamps. The LDO ground current is known to be I ground 10 milliamps, while the LDO junction to case and case to ambient thermal resistances are theta JC and theta CA respectively. The ambient temperature is 25 degrees Celsius, and the incoming supply voltage is at most V power equals 3.7 volts. So question D says, find the maximum temperature of the LDO package, TC. So for this question, we want to sketch the like thermal circuit because we need to actually calculate what the case temperature is. So we need the actual thermal circuit to do that. So what would be the components in this thermal circuit? what would be the thing that generates power or dissipates heat? Yeah, what components would there be in this? So if you read the question, it tells you that the LDO, it tells you some parameters about the LDO. And so the LDO is the device that supplies power. And then you've got it gives you the junction to case and case to ambient thermal resistances. So what we can do is just draw the LDO as a current source, because that's how it's modeled in the thermal domain or whatever. And then you've got your two resistances there, so theta JC and theta CA. With drawing these, sometimes he'll make you draw more complex circuits. The trick, thankfully there is a trick for drawing these, and it's pretty consistent, which is just that for these theta whatevers, you want to make sure that the last letter connects to the first letter of the next theta or resistance. So in this case, since C is the last letter, that has to connect to the CA. I know there's only two, but there can be questions where he gives you more. And so you would need to figure out what each node, like what thermal resistances go to which node. And that's a trick for doing it. So it hasn't failed me yet. And then you have the ambient temperature at the other end of that resistor, so TA. And then you can just use nodal. So this would be P LDO. And it asked for TC. So that's equivalent to this nodal temperature, the temperature of the case. We also need to, so we have TA, we have both of these thermal resistances. What we need to find is PLDO. So in the lectures, you're taught how to calculate the power dissipation in an LDO. So there's V power, VCC, and then ground and ICC. So PLDO is just V power minus VCC times ICC, and plus V power times ICC. So you pretty much consider every voltage drop and every current associated with that voltage drop. So that's 3.7 minus 3.3 times 800 milliamps. Yeah, that should be I ground. I just realized. Yep, thank you. My mistake. So 3.7 times I ground, which was 10 milliamps, I think. Yeah. So this should be, oh yeah, 800, so 0.8, yep. Cool, thank you. So subbing that into the calculator, that gets you 0.357 watts. Now we can do nodal analysis. So if we do nodal at node TC, so the current going in, which is PLDO, is equal to the current going out, which is TC minus T ambient divided by theta CA. So TC minus T ambient, there's a lot of arrows, divided by that resistance. So you don't actually need theta JC, since the current is just dictated by PLDO. So this makes it a pretty straightforward calculation. TC is what you want to solve for, actually. So PLDO theta CA equals TC minus TA, which gives you that TC is equal to TA plus PLDO times theta CA. Great. So that, so putting in TA is 25 degrees. You can use degrees of Kelvin. It actually doesn't matter. 0.357 times, what was theta CA? 50 Kelvin per watt. So TC is 42.8 0.85 degrees Celsius. Yep, that was part D. Any questions before I do the last question of this paper? Nope, all good. So part E, the present design is not efficient in delivering power to the load if the desired output signal is DC-free. Also, the amount of AC power to the load can be substantially increased. The load resistance to the power supplies are given and cannot be modified. So you can't modify RL. Modify the design to increase maximum AC load power. I guess I'll talk a bit about this question contextually. So why is it not efficient in delivering power if there's a DC signal? If there's a DC current that runs through a speaker, that doesn't actually contribute to like the audio output, since it's DC and audio is frequencies. And depending on the speaker, it can actually damage and break the speaker. So it's actually not good to have DC in your output signal for an audio amplifier. So you want to get rid of that DC. And obviously, is there DC? Yes, because the single supply. So if you think about the square waves that get generated, they go between 0 and VCC. So VCC and 0. So that obviously has some DC component that will go into the speaker and will be bad. The other thing that it wants you to do is, or wants you to fix, is the maximum AC load power. So how can we maximize the load power? What's the equation for like average power? Anyone? Sorry? Yeah. V squared on 2R. So V out squared on 2RL. And yes, it's in the context of a resistance because our load is modeled as a resistance. Like I said, in reality, there's some other inductive and capacitive components, but we're ignoring them for the sake of this question. So it said that RL is fixed and you can't change that. So the only thing left that we can really do to maximize power is the output swing. But it said that the power supplies are given and cannot be modified. So you can't cheese it by like saying, I'll just make a negative supply. So those I think are the main clues as to what the design would look like. So I think that there really is only one main solution that you can come up with, which is to use something differential to get that voltage swing, because when it's differential, you can effectively just double your output voltage swing. Yes, question?
Can we use that formula for, because our output is square wave, right? But isn't that derived from a sinusoid? Because there's like √2 and stuff, and then you square that, you get the 2.
Yeah. So the question was, can we use that? Can we use this V out squared on 2RL in this question, given that the output is a square wave? So like I said, it's not really shown explicitly in the question, but you usually low pass filter the square wave such that you get a sine wave at the output. And so that's where that's really coming from. I guess you're just kind of supposed to see it. I think in the lectures as well, he also draws the output of a class D stage as a sinusoid. So you would go from those diagrams, I guess. But yeah, that's why I'm using V out squared on 2RL. It's because I'm just assuming that the output is a sinusoid and not a square wave. So yeah, typically there'll be some sort of low pass filter at the output, or I've heard that you can use a speaker impedance as the low pass filter. And you would want to filter out everything but the audio bandwidth, which is typically 0 to 20 kilohertz. So that would be the cutoff frequency of your filter. Yeah, cool. So yeah, so that's why I'm using that equation. That's why it applies. Otherwise, you would have, if it was a square wave, then you would have the V out squared on 2RL of all the other components, frequency components of the square wave, which, because it's a Fourier series, right? Which I mean, yeah, they will contribute somewhat, but yeah, I'm just assuming single tone sinusoid. Yeah, I mean, in any rate, you don't have to use this. Like for maximizing the power, like the solution, like it doesn't matter if it's a square or a sine wave. If you maximize the, if you double the voltage swing, then you quadruple the power, and that applies to square waves and sine waves. So the first harmonic, yeah, the fundamental, yeah, it'll be dominated by that. But yeah, just assume it's a sine wave for simplicity. It's an audio amplifier, so you get sine. And that sine wave will also have a DC component, so that's bad. We want to fix that. So yeah, so the only really option that we have, since we can't change the supply, we can use a differential scheme to do the increase the output voltage swing. So what that looks like is you can use a bridge coupled amplifier like this. So you've got your microcontroller here. You've got complementary outputs, so X and X bar, and one of them. So you've got your inverting buffers, and that will go to the output stage. And oh yeah, this will go to ground. Is there any reason you need two buffers? Well, the question, where is the question? Oh, whoops. The question just has an inverting buffer bit before the power stage. I'm assuming this is just so that, just to buffer the input from the microcontroller so that you get, yeah, so the microcontroller isn't like loaded by that output stage. So that's why I'm drawing two of these buffers. Right, are you saying, well, yeah, are you saying like, why not just have one buffer splitting into two? I guess you could, as opposed to one. Yeah, I guess you could, but but then the rise time is going to be dictated by both of the capacitances, so of the gates. So it'll be those two capacitors in parallel. So you actually get, if CG1 is equal to CG2, then you'll get double the rise time. And assuming we want to keep the rise time the same, then you'd have two of those buffers there instead of one. So yeah. Yep. I think it's probably not an issue if you draw one there. It's not really the focus of the question. I think you could probably get the marks if you just did one buffer splitting into two gates. But yeah. So you would have this sort of guy going, and then your load resistance sits in between these. So that's your RL, and these would be your other buffers that go into X bar. So how this circuit works is when X goes high, so when this goes high, these buffers go low, and so that turns on this transistor, and likewise, these will go high, which turns on the NMOS instead of the PMOS. So the current flows from VCC to RL, and so like this. So pay attention to the polarity. When the node goes low, so this node goes high, that means that these buffers on the left will go high, and these buffers on the right will go low, which means that on the left side, the NMOS transistor turns on, and on the right side, the PMOS transistor turns on, which means that current is going to flow like this way, where the polarity is that. So the polarity is flipped. So it's like a bipolar voltage output, in the sense that when X is positive, the polarity is felt one way, and when X is negative, the polarity is felt the other way. So if you think about what the voltage across RL is going to look like, VRL, doesn't matter which way you take it, it's going to be, instead of between VCC and 0, it's going to be VCC and minus VCC. Obviously, assuming you can, neglect the transistor on resistances or whatever. But yeah, so instead of going, whereas like before, you just had this between VCC and 0. So you've effectively doubled your output voltage swing, which does what to power times 4. That's right, because it's proportional to the square. So you've increased, so you've quadrupled your average power dissipation, and you've gotten rid of DC because, well, obviously, well, it should be obvious that this, from this diagram, that there's no DC component of that sine wave. It's just a single tone. Yeah, and that's it. That's the paper. Does anyone have any questions about this paper in general, or the course, or anything? I'll do my best to answer, but I'm not the greatest. Yes. The best way to study for the final. Ah, yes. It is a valid question because his finals, Torsten's finals, are a bit not conventional. I think you should do at least several past papers to sort of, not for the purpose of rote learning, but more so to get yourself in the headspace or the mindset of like how to approach these questions. And what I would do is I would at least try and avoid looking at the solutions as much as I can until I actually attempt the problem, and more focus on like stating assumptions, like stating what you think, and moving on from there to like justify whatever design decisions you make or how you model a circuit or something like that. I think that's probably a good thing to want to practice for his finals, because like I said, most of the marks will come from Torsten looking at your answer and seeing that you understand the problem and like what sort of nuances there are. And even if you model it differently to him, as long as your justification is sound and it makes sense, it should be okay. Like I said, there's multiple ways to solve or to approach his questions. Sometimes there's like one main one and the other ones are kind of but yeah, in summary, I would just try doing several past papers to get myself in the like mindset, but just keep in mind that like cramming as many as you can usually won't help that much, since the questions are going to be completely different. It's just going to be based on you applying your intuition on the day. Yeah, that being said, he's a fairly lenient marker. It's actually 3 people doing the marking, because your exam's like on the last day or something, and it gives him like a weekend before he has to submit the marks. So he's gotten a couple of the more experienced demos to help with marking, but they're all very fair markers. So yeah, anyone else? Yes.
The exam's open book. What kind of notes would you recommend bringing in?
Yep. Oh, perfect question. So the question was what notes to bring in to the exam since it's open book. What I did was well, if you're a diligent student and attended all the lectures, you should have lecture notes for all of his lectures that you made. I just printed those out and into like a big binder, or not binder, but like, yeah, sheets of paper. And I just brought that into the exam. Honestly, you won't really need to use notes in his exam. You might, for example, in this paper, I remember having to look at the noise margin equation because I always forget how that's defined. Like at most you would do that. Or let's say like you forgot how to draw an instrumentation amplifier. There you go. You can look at your notes for that if you know where it is. So like, honestly, it's up to you what you bring. Personally, what I did was I just brought in all my notes that I made. But I would try and avoid looking at notes during the paper because it can consume time. And, you know, you might not even find what you're looking for. Like only bring in your notes if you absolutely know where every like thing is. Like I organized my notes in accordance with weeks, and I knew what topic each of the weeks was, so I could easily just flip to whatever notes I wanted to look at. You can print his summary slides. It's also fine. I think he does, you know, very short summary slides for each lecture. But yeah. Hopefully that answers your question. Yep. Cool. Online people. Nope. Yeah.
Explain how does the pull-up resistor actually?
A pull-up resistor.
Yeah, I have
What?
an issue trying to understand. Like when your input is like high, right?
Yeah,
And you try to pull high to another high. Like I don't really understand how that actually works.
Yeah, so I'm assuming you're talking about like this sort of thing where you have.
Without a BJ.
Huh?
Without
without a BJT.
Yeah, just resistor.
So
Like
in
you
what
have
con
like two NAND gates, and they're like different power supply. CMOS and TTL and stuff.
right. And then so
And then
are you talking
just
something
one
like that?
resistor up to like the higher DC state. And it's just like that.
Like that?
Yeah, that.
So I don't think that classifies as a pull-up
No, we can look
resistor.
at tutorial 2.
Tutorial 2.
Yeah, you can look at tutorial 2. That's when I last.
Yeah, I'll have a look on my. Yeah, I'll have a look. Subjects. Oh, but thanks everyone for attending the crash course. Same with you online people. Yeah. Are you talking about this or? Yeah, I should probably just wrap up the thing because it's been over 2 hours. Thanks everyone for joining. Yeah, I'm gonna stop sharing my screen. Yeah, am I just good to call it there? Yeah, all right, thanks everyone for attending. Good luck for your finals. You'll do fine. Yeah, let's do it. Yeah.